Hello everyone and welcome to this WaveJudge Wireless Analyzer Wi-Fi support presentation. My name is Markus Siurumaa and I'm the WaveJudge Solutions Manager. And on the line we have also Dr. Xin Zhao from WaveJudge R&D team. In this presentation we will give you an information why WaveJudge is essential, basically a must for Wi-Fi testing and troubleshooting. Please enjoy. Okay, so in this first slide, let's have a look for Wi-Fi standard evolution. So this slide gives you the timeline of the IEEE 802.11 Wi-Fi standard. The latest commercial version which is available is based on 802.11ax, which is called as Wi-Fi 6E. As we can see, the Wi-Fi 6E has been launched around mid-2021. The latest development version is called 802.11be, which is called as Wi-Fi 7. Wi-Fi 7, it's the hot topic amongst the basically all Wi-Fi chipset, device and access point makers, especially on the R&D labs at the moment. All the development on Wi-Fi is basically focusing on Wi-Fi 7 at the moment. So in this slide, we can see the key enhancements when we go from Wi-Fi 6 to Wi-Fi 7. So basically, in Wi-Fi 7, the maximum throughput has been increased from 9 gigabytes per second all the way to the 46 gigabytes per second. So that is a huge increase on the max throughput levels. And this is basically made possible with a wider bandwidth on a 6 gigahertz frequency, which is 320 megahertz. Then spatial streams has been increased from 8 to 16. And then one of the key one key feature with the Wi-Fi 7 is the Multilink operation MLO, which is enhancing the throughput dramatically by enabling the link aggregation for the devices. So devices can be utilizing multiple links at the same time. Then on the OFDMA front, the enhanced resource allocation has been implemented on the Wi-Fi 7, and preamble puncturing as well as the multiple resource units called MRU are one of the key features around that, the enhanced resource allocation. And also the HRQ process has been enhanced as part of the Wi-Fi 7 standard as well. So basically, when we call that the higher throughput, the higher modulation and more advanced features, they always mean the higher complexity. So to be able to solve complex issues, test tools basically need to support and provide such capabilities so that the problem areas can be deep dived into even the smallest details. So this sets a high demand for the troubleshooting capabilities of the test instruments and test tools. So WaveJudge Wireless Analyzer. So WaveJudge Analyzer makes it possible to analyze and troubleshoot even the most challenging Wi-Fi scenarios, which makes it a must for all customers developing the Wi-Fi 7 device. WaveJudge features and flexibility makes it future-proof for Wi-Fi as well as the cellular test solutions, especially in the changing environment, and this makes the WaveJudge a test solution for years to come. With WaveJudge hardware, user can collect both Wi-Fi as well as the cellular signals over the air from any test system. But this WaveJudge doesn't support only the kind of a hardware-based solution. WaveJudge software-only operation enables the IQ capture import from basically any of the other keysight test solution providing the IQ capture. We can and some of those to say the UXM, network emulator, PropSim channel emulator, and the VSA. So next, Dr. Xin Shao will give you a WaveJudge demo where he will showcase the capabilities to analyze and troubleshoot various Wi-Fi features. Please enjoy.
In this presentation, I'm going to first, just show the generic solution of the WaveJudge support to Wi-Fi from the very start to Wi-Fi 5, 6, 7. Basically, it's everything up to Wi-Fi 7. Our baseline GUI would be very similar to what we have for the LTE and the 5G NR. We have a fundamental frame list. Basically, is the fundamental information for each burst of Wi-Fi, and we have the message list with the decoding with all kinds of KPI, and we get Constellation plots. We get time domain charts. We get a very unique 2D physical, and we have the baseline IQ. We get a spectrum, power spectrum, and we also have the we can show you the channel estimation for each transmission for each layer, and also we can show the EVM per each sub carrier, each of them symbol, and on the each layer. So let me give you an example to what we have here. This is a transmission of through the Wi-Fi 6 IEEE AX. How you configure the capture? How you configure this one? Is we have the concept called a cell. It's Wi-Fi. It's a carrier for Wi-Fi. So we call the Wi-Fi cell. And for the cell, we can configure we can configure the multiple ports. And in this capture, we have 4 ports. And this port is configured as 160 megahertz the bandwidth, and we configure the sampling rate with 160 megahertz. Anything larger than 160, in this case, for example, it can be to 300 megahertz. Anything larger or equal to 160 would work. You need to configure the either automatic or with AX to decode Wi-Fi 6. If you want to decode Wi-Fi 7, you should need to configure with with BE. And our platform supporting both directly from WaveJudge hardware, which including the 5000, with the one is 40 megahertz, 45 megahertz band sampling bandwidth maximum. It's what we call the 4G car RF car, or our 5G RF car, which can support to set the sampling rate can up all the way up to 800 megahertz. And with our 5900 also we support up to 800 megahertz. So we have the 3 platform, 5000 low band, 5000 high sampling rate, and 5900. And this is one way we would get captured. The other way would be through the IQ import. The IQ can be captured from the multiple platform. I will show you what the platform we support today, which basically covers almost every IQ recording capture platform that's within the Keysight. We can do support. That's what we support. Anything with the Glacier, just VSA 8960 as any format can be captured there. We support. So it's including CSV, will be text file, text IQ. SDF will be the compact binary IQ. HDFI is next generation binary format, and the binary this is for some legacy binary format within Keysight. We also support like a UXM and the PropSim proximity channel emulator, and the PWSD, the pathway platform. So this capture we show here is through EEA60 platform within which is a Keysight IQ recorder. So after you get an IQ, we will decode each burst within the IQ, each valid burst within IQ. For example, in here, if we see each peak within the time domain, each peak will be it's a transmission. So we just decode every one of them from the UE to the AP and from AP to UE. It's whatever you call it. But every transmission within this period, within this bandwidth. And for the transmission, we support for the Wi-Fi 6, we support all the both Wi-Fi 6 and Wi-Fi 7. We support all the way to the 4096 QAM. So let me show you what we have here. If you transmit this in this transmission, is a downlink. This is from the AP to UE. You can zoom in our 2D power charts. It will shows all the small parts of this transmission. It from the first will be the legacy STF and the legacy LTF, long sequence and the short sequence for the short sequence preamble and long preamble, and then we get to the LSEG and the repeated LSEG and HESEG A, HESEG B. All these are signaling. We decode every single of them, and then based on this signaling from the LSEG, HESEG, HESEG B, we schedule the data on the follows in this burst, and also we also shows it's called HE, basically it's Wi-Fi 6 short sequence and the long training sequence to help to doing the channel transmission. We also have the pilot here. It's the phase tracking tones for this whole burst for this data session. So this is and also the color is our way to scheduling, and the brightness will be power in this 2D power charts. And we have the constellation, which basically is equalized data, how they show the constellation plan. In this case, it's 1024 with 2 layer. Number of layer we can show here. It is a 2 layer. Number of layer we show here is 2 layer. We can show this constellation either to all layer or layer 0 or layer 2, layer 1. So this shows which layer, the constellation for each layer. This is constellation, and also show for each point on this constellation plan. Which shows the EVM per subcarrier, or it's also for per layer. It can be shown as per layer, and we also show the channel estimation, which we can see from the beamforming phase and the beamforming power. So this basically beamform on each subcarrier. This shows our channel estimation for each layer, or for each UE, and for each transmission TX over each RX. It's right here. So it's this plot is extremely useful if it's beamforming. You can see for this case the beam each beam has its on the different carrier, different subcarrier. It has a different phase, which basically is tell which can generate a beamforming pattern for each subcarrier. That's probably many users would really really want to know. And we also show the spectrum here and the channel transmission. For this case, it has two transmission ports. So we show the port 0 and the TX0 and the TX1. This is for UE0, and this is for UE1. So we have that. And so this basically is this of the everything we can offer here, and on top of that, we will get a summary for its whole capture. For this capture, for example, we're getting it's from the 5.25 gigahertz with 160 megahertz bandwidth, and our downlink EVM is roughly minus 38 dB, and uplink is minus 25 dB. And the throughput, you can see the downlink throughput, the peak throughput is 2.4 gig. And for the uplink, the peak was the 2.4 gig Mbps. That means it's fully highest MSCS with the 160 megahertz with 2 layer. So this basically is everything we have for the decoding. But we have full API here for each transmission, and you can choose from here. It can be anything from the PHY RF all the way to the higher layer. And it's also, for example, it's pretty important if we want to write the transmission MAC address and receiving MAC address. That would uniquely decide which where the target is and where the receiving address is, and also have the BSS ID for transmission as much as we can do. In this capture, we can see the uplink power is a little bit low, and it's using the highest MSA. That's why we cannot decode the data session of this capture for the uplink, because it's cabling problem. WaveJudge can show this kind of problem through just right away. One of the important feature we have here is we can show the message list with category. For example, in this case, we can only show the control messages, which will be including the ACNAC, request send, and the clear send, and also the triggering. I'm not sure if any management here, or it's only Bacon message here as management, the control. And we also can do can filter out, which can through our filter. So which is called from the WaveJudge filter. And for example, if I want to get all the ACNAC, I just need to set the filter, block ACK. And in this case, because it's Wi-Fi 6, I also want to see the triggering, which trigger would be it's really the what AP send a message to the UE to make the UE respond based on the trigger. So this is a very unique feature from Wi-Fi 6, and also a very important feature for Wi-Fi 7. So it just now I set the ACNAC and the trigger for its capture, and now I can only show this filtered message here, along with my probably my MAC and the PSTU and the frame. It's probably so now I have my data and the trigger and the block ACK for each session. So everything's filtered out. So you can, if you care about the trigger, you can double click, and you can get in the full decoding from this trigger frame. You see that you can see that everything is there. Trigger. You see the frame control info, and for each UE, what's the details of each transmission, the signaling. And if you care for the the ACNAC, for example, this it's block ACK. You can really see the block ACK, what's the fragment number, sequence number, and what's the loop like. It's like this case, everybody is ACK. Everybody is ACK. So this basically, and also for each data you can see you can get decoder, full decoder too, and with sequence control with a free sequence number, fragment number, and you can check this ACNAC later with those ACNAC knowledges. This is basically covering our decoding and filtering, and we show that for each transmission, of course we show the EVM and the power of it. It's either from the hardware or from IQ importer. We show a pretty accurate measurement on that. So it basically it's everything we think is important. Like for example, FEC correct bits, the modulation type, and the MIMO type like this is beamforming. It's very important. You know it's beamforming, so you can see how it's how the beam for each subcarrier how they generate. And we also have like a RU index. Basically, it's a concept of the Wi-Fi 7, but it can be applied to the Wi-Fi 6 as well. So like this case, it's it have the it's basically the whole spectrum, the whole spectrum, the whole bandwidth has two RU, 1996. Let me see the the number of resources. Basically, it's 1996 tone RU. We have two RU in within this 160 megahertz. The RU1 is for the UE1, RU2 is for UE2. They have the station ID, STA IDs 14 and 13, and so it's basically, and each with the data rate the 1.2 gigahertz, 1.2 GPS. So that's basically everything I can cover for the basic support, and this is a Wi-Fi 6 capture. Let's move on to the Wi-Fi 7. Wi-Fi 7 basically is just extended version of Wi-Fi 6 with some unique addition. Let's us talk about it one by one. First of all, I'm going to talk about the Wi-Fi 7 decoding. So let me open a Wi-Fi 7 capture. So this is a Wi-Fi 7 kind of like they call it deep scanning capture. It's recorded by hardware, and we get this capture through the IQ recorder, same platform, Keysight EE680. And this is 7 gigahertz with 320 megahertz. It's full bandwidth, but they scanning from the MCS from 0 all the way to the 13, and the 13 is the one with the 4096 QAM with the highest coding rate. So with this, you can see the number of subcarriers, almost 4,000 subcarrier, and the data rate. It's only one layer, but the data rate can be as high as almost 2.9 gigahertz Gbps, and we get all these key statistics right here. It's you can see our EVM is minus 40, almost 44, almost 45 dB, and the uplink throughput is a throughput. The peak throughput is 2.88, basically 2,882 Mbps. And we also provide like frequency offset. It's basically from the RF mismatch. And we also provided it's not only just peak, also as average throughput, which probably is more important statistic in a true test. It's like this. It's even the peak throughput is almost 3 Gbps, but the average throughput only 60 Mbps because we're doing a lot of the small MCS. So this is Wi-Fi 7. This is a very simple one. So it's just one. SU is SU PPDU, only one user, one layer. Let's move on to some more interesting MRU. Let's open one MRU capture. MRU capture is MRU is basically it's MRU. So it's just basically some RU actually has multiple RU base RU type. So in this case, the first RU. First UE basically is a UE0. It's actually using they call it 106 plus 26 RU. So it's actually 132 number of RU, and this one is RU index is 1. We can see RU index 1, and this is if you zoom in, you will see this is the upper part of this spectrum is 106 RU, and the middle part is 26, but we call it 106 plus 26 RU, and we call them MRU. This is something new in the Wi-Fi 7, and I think it's a good thing to have because it makes the spectrum more flexible. This OFDMA system is more flexible to use so to make the AP to be more flexible to use the whole more effectively to support multiple UE with so meeting each UE's request. So the second UE is a regular 160 106 tone RU. So it's MRU, and we also support the what they call the larger than 80, so what they call the large MRU. But the large MRU, I think, is more related to the puncturing, spectral puncturing or preamble puncturing, you call it. And we will show it a little bit later for the large MRU. But we before we move into this mu MIMO or spectral puncturing, I want to show some feature WaveJudge uniquely can support for the MLO. So it's a multi-link operation. In this capture, we still use the same platform, but that platform we're getting very wide. It's very wide sampling with very wide sampling rate, which cover two carrier. One carrier is at 5.80 gigahertz. A second carrier was at 5.975 gigahertz. We take the capture. We basically just import capture through our platform, IQ import platform with SDF, and enable the MLO IQ import with this option. With this configuration, cell configuration, we load this capture. This capture is 400 megahertz, 400 Mbps, 400 megahertz sampling rate bandwidth, captured at, and we import it, and we get it. We get a two carrier to decode it. Let's we can show the summary here. We can show the port 2 for the cell 2. So you can see from this, the carrier 1 or AP1, not AP1, it's carrier 1, is at 5.80 gigahertz, 20 megahertz bandwidth, and its throughput, peak throughput is 155 Mbps. That is for the and the average is 120 about, and the BSSID is this number. For the carrier 2, we're getting similar thing, but with a little bit less throughput. The peak throughput of about 52 Mbps. We can see from spectrum, actually the carrier 1, the low with the lower frequency, the carrier get better spectrum. The second one actually with a little bit less RF. So it makes sense. It's the carriers 1 has better throughput. We show this is because in the ML is very important to measure if you can measure the alignment with two carrier. And with this approach, WaveJudge actually hardware can capture for two carrier at the same time too. So either with IQ import or with hardware, we can decode all carrier at the same time. So we can really using the timestamp right here, timestamp, to align these two carrier or three carrier or even maybe four carriers together, and we can measure the alignment in the timing, frequency, and their signaling. So we believe WaveJudge solution can provide a huge benefit to people develop the MLO. If this is from the carrier 1, you see the carrier 2 here. We also can make it to make it center as the carrier 2. You can see the carrier 2 is here, and this is carrier 1 looks like the other side. So and also we decode the in this case. You can see this is actually 4096 QAM, even it's MCS only 12. So we perfectly decode it with and with frequency. You can see that these two carrier with one is with -8 kilohertz, and the other one with 34. That means these two carriers not frequency aligned, because this is from one RF recorder, one single carrier, one single capture. So this is really just from the it can be almost certainly is from the transmitter. So this actually already disclosed one problem with this MLO operation for these two carriers. And also we decode all the way to the up. So we in our next new build, we'll also provide the IP decoding from this data. And we also shows the beam phase, beam power. Let's go back to port 1. And also I forget to mention one thing. We always can show the decoding. So it's basically it's 5-level decoding. It's always there. You can from here, either from here or you double click it. It's from there. It's from this all the way to the Mac, or even each body, each data session. You get the payload. Okay, so it's pretty much for the MLO. Let's move on to let's show one capture with MU-MIMO. So I open a few MU-MIMO. This basically is a 2 one-layer data. This is multiple UE, but for the lower portion of the spectrum, it's actually 2 UE. One UE transmit and transmitter TX0 transmission chain 0, and the other UE this is from 0, and the other UE transmitted on the TX1. So these 2 UE they transmit at same frequency, that means same time, just on the different transmission chain. So they generate a MU-MIMO, generate multi-user MIMO. So we can show this on for example, the channel transmission here, and if you shows and for each port RX0 and RX2, yeah, this shows and we also could show for each UE, we can show the EVM here, EVM for each UE for each user, and the constellation for each user. So the puncturing basically they just using scheduling based on the scheduling, they just allow the UE or the AP transmitting on portion of the carrier bandwidth. Like in this case, I should show the. It's good. I should go show the EHT PVD view. So this was, for example, this one is it's using this is a 160 megahertz capture. I think it's 160. Let me see. It's 160. Actually, it's from here. Oh, it's 320. Oh, 320 megahertz. So you can see there's a full portion of the 480 megahertz. 480 megahertz, you get spectrum, and only part of them used. And you see if we go to the saturation range to all. If you look at all the signaling portion and the preamble portion, they only transmitted on the non-punctured portion of the spectrum. So all the color is what we believe should be scheduled, and all the brightness, if I zoom in, is what I believe it should. It's really the power, the white brightness. So it's a perfect match our scheduling in this capture. This capture is from the Signal Studio, so I can import from Signal Studio. Yeah, you see this is for the Wi-Fi 7 is very flexible. So this is a good example this is for non-OFDMA. If I can find a OFDMA puncturing, that would be good. Let me see if I can find one. Yeah, this is OFDMA puncturing. Yeah, this is OFD. It's multiple UEs and only use certain portion of the spectrum. All the color is where it's transmitted, and through the whole time. And if you want to see which one is which, just click it. It'll be highlighted. And that's pretty much what I want to introduce today.